Little's law is the key factor in any queuing system. Having a good understanding of this law will allow any operation to control the amount of chaos in their system. The law states that the average length of a queue is equal to the average throughput times the average working process. Or in this case, queue time is equal to the average length of a queue divided by the throughput. Let's take Walmart for example. Their express checkout is an attempt to control the chaos. By reducing the inventory, in this case the number of items in each cart, they can achieve a more stable throughput, which in turn leads to shorter queue times. Let's assume that customers arrive to the queue every 2 minutes. Since there are 3 people in line, we can assume each person has an average waiting time of 1.5 minutes. As each person exits the queue, the next person's waiting time is reduced by 1.5 minutes. Each person entering the queue has a queue time equal to 1.5 times the number of people in line. The next person times goes from 4.5 minutes to 3 minutes, and the newest person in line has a waiting time now of 4.5 minutes. Unfortunately, as with any system, there is random variability that cannot be accounted for. There can be a number of errors that can occur to cause the system to process slower than its expected rate. In this case, the culprit is the price discrepancy between customer and system. Here, you can notice another discrepancy that slows down the system. Now the waiting time of the 2 new entrants to the system has been increased. So, to recap, you only have to change one of the characteristics to have an influence over the other 2. In a stable process, if you want to reduce queue time, you have to reduce the inventory. In order to reduce the inventory, you reduce the rate at which work is introduced into the system and control it at a rate equal to the throughput. You can also cut queues in half or stop introducing work for a period equal to half of the queue size. Knowing these laws will help you effectively control any chaos in any system.